Hello, and welcome to General Astronomy Lecture 10, The Formation of the Planets. To understand how the planets, asteroids, and comets formed, we start by considering a cold and low-pressure solar nebula before it was warmed by an emerging protosun. At the low pressures that prevailed, a substance does not form into a liquid state, but must exist as either a solid or a gas. As an example, you can refer to this figure, which shows a dust grain of the sort that would have been present throughout the solar nebula. Other substances in the early solar nebula would have been in the form of small ice crystals like snow, although at high temperatures these ices would evaporate to form a gas. Together, these solids, referred to as ices, dust grains, and ice-coated dust grains, were mixed with gaseous hydrogen and helium, but things began to heat up. So this highly magnified image shows one of those microscopic dust grains. They came from interplanetary space. It entered Earth's upper atmosphere and was collected by a high-flying aircraft. Dust grains of this sort are abundant in star-forming regions like that shown in a previous lecture. So these tiny grains were also abundant in the solar nebula and served as the building blocks for the planets themselves. The planets began to form after the solar nebula collapsed and flattened into a disk of perhaps diameter of about 200 astronomical units. The churning and mixing of the gas in that solar nebula should have ensured that the nebula had the same composition throughout, about 98% hydrogen and helium, and then 2% heavier elements. How then did the terrestrial planets end up so different from those of the Jovian planets? Well, the key clue comes from their locations. Terrestrial planets formed in the warm inner regions of the swirling disk, while Jovian planets formed in the colder and outer regions of our forming solar system. So we first need to understand the condensation temperature, which determines when a substance forms a solid or a gas. If the temperature of a substance in the solar nebula is above the condensation temperature, this substance is a gas. On the other hand, if the temperature is below the condensation temperature, the substance would solidify or condense into tiny specks of dust or ice frost. You can often see similar behavior on a cold morning. So the morning air temperature can be above the condensation temperature of water, while the cold windows of a parked car may have temperatures below that condensation temperature. Thus, water molecules in the warmer air remains a gas, that being water vapor, but it may form solid ice particles or frost on your colder car windshields. So that gives you an idea of how this might work. So you'll have a gaseous state near the warm protosun, and you'll have more solid ices further away. The temperature in the nebula varied significantly, rising above 2,000 degrees Kelvin closer to the hot protosun, and dropping below 50 degrees Kelvin in the outermost regions. With heat from the emerging protosun, the solar nebula was radically changed into two distinct regions. These regions, inner and outer, had very different properties and eventually formed different planets. So for the inner region, which was the planets that were made out of rock and metal, in the hot inner region of the nebula, only substances with high condensation temperatures could have remained solid. These rocky and metallic materials, in the form of solid dust grains, eventually formed much of the rock and metal of the terrestrial planets. Hydrogen compounds, such as water, methane, and ammonia, remained as a gas, so they could not condense into solids in the warmer inner regions of the solar system. So basically, it was so warm that only rocks and metals could solidify. Everything else was gaseous and could not help build the planets that we know to be the terrestrial planets today. As for the outer region, well, in the area between present-day orbits of Mars and Jupiter, the temperature had dropped below about 170 degrees Kelvin. In the low pressures of the solar nebula, this is the condensation temperature at which water vapor forms ice. One aspect of this, what we call snow line, which is the distance from the sun at which water vapor solidifies into an ice or frost, is that beyond this line, the solid ice particles can join with the rocks and metals to form a more massive planet. Right, so in the inner parts of the solar system, we only had rocks and metals. But now, beyond this snow or ice line, we have icy materials to help build the planets. So this can give us an idea as to why the outer planets are bigger. And we'll get to that more throughout this lecture. So even further out, there are, at even cooler temperatures, methane and ammonia ice lines as well. So basically, the further out you go, the more material you have to build some planets. So here's a great graphical representation of everything we're talking about. So the graph on the left shows how temperatures probably varied across the solar nebula as the planets were forming, and the present-day position of the planets. Note the general decline in temperature with increasing distance from the center, right? So you see, here's basically where the sun would be, or the proto-sun, and the further away you move, the colder it gets. So between present-day Mars and Jupiter, which is right here where you see this blue dashed line, the snow line marked where temperatures were low enough for water to condense and form ice, beyond about 16 astronomical units. And then you can see also where that 16 astronomical units is where methane can condense and form more ices. So the idea is here, so right where the snow line is, the snow line happens to separate our terrestrial planets from our Jovian planets. So this plays a huge role in the formation of our planets. Now on the right, it just shows a nice figure. So terrestrial planets formed inside of the snow line, where the low abundance of solid dust grains kept the planets small. The Jovian planets formed beyond the snow line, where solid ices of water, methane, and ammonia added to the masses to build larger cores and attract surrounding gas. So now we have kind of the stage being set up for how this all comes together. So in our last lecture, we talked about how we go from just a random cloud out in space into a disk forming a solar system, and now we know to an extent about where the planets are coming from. So let's dig into this a bit more. The frost line, or the snow line, marked the key transition between the warm inner regions of the solar system, where terrestrial planets formed, and the cool outer regions where Jovian planets formed. Inside the frost line, only metal and rock could condense into solid seeds, which is why the terrestrial planets ended up being made of metal and rock. Beyond the frost or snow line, where it was cold enough for hydrogen compounds to condense into ices, the seeds of the planets were built of ice along with that metal and rock. Moreover, because hydrogen compounds were nearly 3 times as abundant in the nebula as metal and rock combined, the total amount of solid material was far greater beyond the frost line than within it. The stage was set for the birth of 2 planet types: planets born from seeds of metal and rock in the inner solar system, and planets born from seeds of ice as well as metal and rock in the outer solar system. From this point, the story of the inner solar system seems fairly clear. The solid seeds of metal and rock in the inner solar system ultimately grew into the terrestrial planets that we see today. But the planets ended up being relatively small in size because rock and metal made up such a small amount of the material in the solar nebula. The process by which smaller seeds grew into planets is called accretion. So accretion began with the microscopic solid particles that condensed from the gas in the solar nebula, so just tiny little particles. These particles orbited the forming sun with the same orderly circular paths as the gas from which they were condensed. Individual particles therefore moved at nearly the same speed as neighboring particles, so collisions were more like gentle touches. Although the particles were far too small to attract each other gravitationally at this point, they were able to stick together through electrostatic forces, the same kind of, quote, static electricity that makes hair stick to a comb. Small particles therefore began to combine into larger ones. As the particles grew in mass, gravity began to aid the process of their sticking together, accelerating their growth into boulders large enough to count as planetesimals, which means pieces of planets. So here we see this general process visualized. The planetesimals grew rapidly at first. As they grew larger, they had both more surface area to make contact with other planetesimals and more gravity to attract them. Some planetesimals probably grew to hundreds of kilometers in size in only a few million years, a long time in human terms, but only about 1/10,000th of the present age of the solar system. However, once the planetesimals reached these relatively large sizes, further growth became more difficult. Gravitational encounters between planetesimals tended to alter their orbits, particularly those of the smaller planetesimals. With different orbits crossing each other, collisions between planetesimals tended to occur at higher speeds and hence became more destructive. Such collisions tended to shatter planetesimals rather than help them grow. Only the largest planetesimals avoided being shattered and can grow into terrestrial planets. So this just kind of shows you what it would look like visually. At first, the material that coalesced to form protoplanets in the inner solar nebula remained largely in solid form, despite high temperatures close to the protosun. But as the protoplanets grew, they were heated by violent impacts that collided with other planetesimals, as well as by the energy released from the decay of radioactive elements. And all this heat caused melting. Thus, the terrestrial planets began their existence as spheres of at least partially molten rocky material. Material was free to move within these molten spheres, so the denser iron-rich materials sank to the centers of the planets, while the less dense silicon-rich rocky material floated up toward their surfaces. This process is called chemical differentiation. In this way, the terrestrial planets developed their dense iron cores. So if you recall, I think it was in our previous lecture, I had a question for you that asked about the average density of a planet. So we have solid cores of heavy material because all that heavy material, when the planets were molten and forming, sank to the center. So our planet doesn't have the same density from surface to core, right? It gets more dense as you go further in as a result of this differentiation. So here I have a great video, or it's a simulation, so this isn't a real forming system, but it's just 45 seconds, and it shows you how you can go from a disk, like how we started out at the beginning of today's lecture, to forming some planetesimals. So let's just take a look and see how some of this material can accrete and coalesce. So you can see now that a lot of the material has formed into these lumps. So these might be the planetesimals that we're talking about. And over time you might see one of them fall into the protosun, or some of them collide, and it's a pretty violent process. And this is occurring over many, many years. But you get the general idea. So there at the bottom you saw two planets come close together. Those two, well, it's hard to narrate. There we go. So those two on the right just collided to form one. So you can kind of see that's just a simulation. So somebody made that video and decided that, with these certain properties, this might be how it looks. But it's a great visualization of what we're discussing, and that's along the lines of what we're looking at in this lecture. So I hope that helped a little bit. The reference is down at the bottom, since this one I just decided to keep in the lecture. So that's the terrestrial planets. But what about the Jovian planets? Well, accretion should have occurred similarly in the outer solar system, but condensation of ices meant both that there was more solid material and that it contained ice in addition to metal and rock. The solid objects that reside in the outer solar system today, such as comets and the moons of the Jovian planets, still show this ice-rich composition. However, the growth of icy planetesimals cannot be the whole story of Jovian planet formation, because we know that the Jovian planets contain large amounts of hydrogen and helium gas. The leading model, which is called the core accretion model, for Jovian planet formation holds that these planets formed as gravity drew gas around ice-rich planetesimals, much more massive than Earth. Because of their large masses, these planetesimals had gravity strong enough to capture some of the hydrogen and helium gas that made up the vast majority of the surrounding solar nebula. This added gas made their gravity stronger, allowing them to capture more gas. Ultimately, the Jovian planets accreted so much gas that they bore little resemblance to the icy seeds from which they grew. Due to the lower temperatures in the outer solar system, Jupiter's large seed mass could capture and retain hydrogen and helium gas. So this picture, where a Jovian protoplanetary core captures gas and grows by accretion, again is called that core accretion model. As Jupiter grew, its gravitational pull increased, allowing it to capture more gases and grow even larger until most of the available gas in its region had been captured. Because hydrogen and helium were so abundant, again about 98% of the solar system's material, Jupiter quickly grew to be more than 300 Earth masses. Farther out in the solar nebula, Saturn would have gone through a similar process. About 1/3 of the mass of Jupiter, Saturn's 95 Earth masses would have taken longer to accumulate, forming a few million years after Jupiter. Uranus and Neptune formed well beyond the snow line, where temperatures were cold enough for additional ices of carbon dioxide, methane, and ammonia to form the bulk of these planets. This model also explains most of the large moons of the Jovian planets. The same process of heating, spinning, and flattening that made the disks of the solar nebula should have also affected the gas drawn by gravity to the young Jovian planets. Each Jovian planet came to be surrounded by its own disk of gas, spinning in the same direction as the planet rotated. Moons that accreted from ice-rich planetesimals within these disks ended up with nearly circular orbits going in the same direction as their planet's rotation and lying close to their planet's equatorial plane. However, the Jovian planets also have smaller bodies called irregular satellites that orbit in the opposite direction, and these were probably captured after the planet was formed. So there are some small objects moving in the opposite direction around these larger Jovian worlds, and we believe that they were captured into orbit, not formed with the planet. The vast majority of the hydrogen and helium gas in the solar nebula never became part of any planet. So what happened to it? Apparently, it was cleared away by a combination of intense radiation from the young sun and the solar wind, a stream of charged particles continually blown outward in all directions from the sun. Although the solar wind is fairly weak today, observations show that stars tend to have much stronger winds when they are young. The young sun, therefore, also should have had a strong solar wind, strong enough to have swept away huge quantities of gas out of the solar system. The clearing of the gas sealed the compositional fates of the planets. We now look at migration, which refers to changes in orbital distances of the planets. So, at this point, we basically have an understanding now of how all of our planets formed. In the inner parts of the solar system, where we only had rocks and metals, the planets formed by accretion, where basically just chunks of rock slowly built up in size, collided with one another to form the inner planets. In the outer parts of the solar system, we have the core accretion model, which is where you still have these solid cores, or what we call seeds, but they became large enough to capture a lot of the hydrogen and helium gas that was out there beyond the snow line. And so that's how we get those gaseous worlds. So now we're going to figure out how the solar system formed its general shape, why we have certain planets in their certain positions. So migration of the planets results from interactions, that is, the gravitational pulls and tugs, between planets in different parts of the forming solar system. Within the first few 100,000 years, long before the terrestrial planets formed, Jupiter's interaction with the gaseous disk of hydrogen and helium led to an inward migration of Jupiter, followed by an outward migration. So it had an inward migration. I don't know if we talk about this too much, but because it's colliding with all this other material out there, it kind of slows it down and it falls inward. So we'll get into this a bit more. But at its closest distance to the protosun, Jupiter actually migrated inward to about 1.5 astronomical units, which happens to be near the current orbit of Mars. With its large mass, Jupiter gravitationally deflected many of the planetesimals near the current Martian orbit. As a result, when Mars eventually formed in this region, it ended up with a low mass of about 1/10 of Earth's mass. In fact, it was the mysteriously low mass of Mars that prompted this analysis of Jupiter's inward migration. Even more, inward than outward migration of all the Jovian planets, which we call the Grand Tack model, also solves a long-standing mystery involving the asteroid belt. So basically, what I'm getting at is Jupiter was kind of the bully of the solar system. It moved inward while it was forming, and it basically took all the material where Mars will have formed and kind of kicked it all away. So that's why Mars is so much smaller than Earth or Venus. It's because Jupiter migrated inward, kicked all the material out before moving back, and then Mars started to form, but it didn't have as much material there as it would have. So that's the general idea. But this does, again, also explain the mysteries involving the asteroid belt. The asteroid belt contains rocky objects typical of the inner solar system, but surprisingly, it does also contain icy objects expected to have formed beyond the asteroid belt. In the Grand Tack model, as both Jupiter and the other Jovian planets migrate outward, they deflect planetesimals inward to form the asteroid belt. So this kind of has to do with some of like Newton's laws, where you have an equal and opposite reaction. So we have the bigger Jovian worlds moving outward in their migration, so they're kicking things inward. Some of these planetesimals come from the inner solar system, but some also come from much farther out beyond the snow line, providing a very natural explanation for the icy objects that are found within the asteroid belt. This early migration, along with the Jovian planet formation, was over within the solar system's first few million years or so. Another type of migration occurred over the next few 100 million years and reshaped the outer solar system. Astronomers have long suspected that some planetary migration must have taken place in the outer solar system. To see why, consider Neptune. At Neptune's current large orbital distance, the timescale necessary to build a planet of Neptune's large size by core accretion model is much longer than the time that the protoplanetary disk was around. So in other words, with how long our solar system was there to form, there's no way Neptune could have formed where it was because it would have taken too long to collect as much material as it has. However, planets grow much faster closer to the protosun, where the protoplanetary disk is denser. Therefore, astronomers suspect that Neptune formed closer in and then migrated outward. This leading theory, the leading theory described here for late migration of the Jovian planets, is based on the Nice model. In the Nice model, the Jovian planets would have all originally formed within about 20 AU of the protosun, even though the outermost planets today, that being Neptune, the outermost planet, lies at about 30 astronomical units. So it must have migrated about 10 astronomical units outward. There was also a disk of planetesimals beyond the outermost Jovian planet at 20 astronomical units, and through gravitational encounters, these planetesimals, on average, were scattered inward. When a big planet knocks a small planetesimal inward, the planet itself is kicked slightly outward. Over a few 100 million years, as numerous planetesimals were knocked inward by Saturn, Neptune, and Uranus, these Jovian planets slowly migrated outward to their current locations. Most of the inward-moving planetesimals even made it close to Jupiter. With its much greater mass, Jupiter did not migrate inward very much, but it did gravitationally fling most of the planetesimals clear out of the solar system. However, a small fraction of these icy objects would not have made it all the way out of the solar system and are therefore currently orbiting at about 50,000 AU from the Sun. These planetesimals would be very loosely bound to our Sun, and gravitational deflections from passing stars would spread many of their orbits into a spherical halo. We call this hypothesized distribution of icy planetesimals the Oort cloud, which formed beyond the objects of our next topic, the Kuiper belt. Gravitational interactions with the planetesimals eventually destabilized planetary orbits, leading to the elongated or eccentric orbits that we see today. With elongated orbits, the planets gravitationally interact with each other more strongly. In many computer simulations, this nearly doubles the orbital distance of Neptune, sending Neptune out to its current distance of 30 astronomical units. as Neptune moves outward, its gravity flings nearby planetesimals to greater distances as well, creating an orbiting collection of icy objects called the Kuiper Belt. The Nice model seems to solve another mystery of the solar system. Astronomers think that there was a cataclysmic period when the planets and moons of the inner solar system were subjected to a short but intense period of large impacts. This hypothesis is referred to as late heavy bombardment. So what could cause a big jump in impacts? Well, in the Nice model, the destabilized and elongated planetary orbits also led to deflections of planetesimals throughout the inner solar system. So this leaves us now at a point where we have a general idea of how the solar system formed, how the planets formed from that disk that the solar system came about in, and now how each planet got to where it was. So in summary, we end with these 3 slides just showing you, again, a visual overview of everything that happened from the beginning of Lecture 9 into this one. So you begin with a large clump of gas. It has a slight rotation in it, so that big ball of gas might get hit with a shock wave from a nearby explosion or something and triggers its collapse. Once it starts collapsing, gravity will assist that collapse and cause it to occur more quickly. But as it gets smaller, just like a figure skater pulling her arms in, that rotation speed increases. And as a result, it starts to flatten out into a disk. So you have a lot of dense material up in the center and less dense material outward. So it starts heating up as things start colliding with one another in the inner parts of the solar system formation, and you begin to heat up enough to form a protosun. Eventually, that material starts to clump up, and you get lots of just dusty debris around, and it's warm enough now to where we can define a snow line, a region where condensation occurs for water. So over time, after a few million years, we have a nice solid protosun formed. The snow line is starting to mark what's going on in the solar system. The first planet to form, as we mentioned, was Jupiter. So Jupiter starts growing in the outer parts of the solar system. It's sweeping out the material. And then over time, Saturn, Neptune, and Uranus form, closer than they are today, though, right? But they start to move outward as they fling materials inward. At this point, the inner planets are still forming. They're slowly building up from planetesimals. Well, then we finally get to the point where we have a present-day solar system. So the Jovian planets migrate outward, as I mentioned, and Jupiter flings objects out of the solar system to form the Oort cloud that you see here in a spherical halo around it. So there's a lot going on here, but this is, again, just a very quick and general overview of the formation of our solar system and its planets. So from here, we're going to take a dive into each planet a little bit more. So we're going to look at the terrestrial worlds and the geology of them, and then we'll talk a little bit more about the outer worlds as well. So as always, thanks for watching and have a great day.